Welcome to Cloud on Air, live webinars from Google Cloud. We're hosting webinars daily. You're watching Into the Cloud, a programmatic approach to go deeper into strategic themes for the cloud business. My name is Charlie Fontaine, and today we'll be talking about autoscaling your Kubernetes workloads. You can ask questions anytime on the platform, and we have Googlers on standby to answer them. Let's get started. Throughout the history of computing, managing workload capacity has always been a concern. The past few years have provided exciting capabilities for dynamically scaling workloads rapidly and cost effectively. Today, I'll be talking about how to manage your application workloads for availability and cost efficiency using the metrics that really matter. Everybody is familiar with this famously bad prediction attributed to Thomas Watson, an early CEO of IBM. I think there is only a market for 5 computers. What few people know is that it's not actually what he said. What Mr. Watson said in the shareholder meeting is that they had sent prospectus about the IBM 701 electronic data processing machine to 20 potential clients. They thought they would get the interest of 5 of them. But instead, they received 18. We often hear this quote and laugh, knowing how important computers are nowadays. How wrong was he? But how wrong are we? Capacity planning is hard. There is always a demand for more computing, as well as a need for cost optimization. Hi. I'm Charlie, and I'm a software engineer at Datadog. I work on integrations with container runtimes such as Docker Containerd and orchestrators like Kubernetes. I also love cheese and rock climbing. If you're not familiar with Datadog, we're a SaaS platform for monitoring. We give our users great insight into their infrastructures and applications using metrics, logs, and application traces. As we support more than 250 integrations, we thrive to offer the best tooling to monitor any type of stack. We also run on Kubernetes and heavily use autoscaling. So circling back on the lesson we learned from Mr. Watson. The lesson is that it's really hard to know what you really need, and even harder to know what you will need. Let's take a brief trip through time. Back in Mr. Watson's days, scaling was super hard, especially as computers took entire rooms. They obviously did not have the same scaling problems that we have nowadays, but adding a new computer could take months. Now, skipping ahead a few decades, we have miniaturized and standardized components, and even if you have not worked or stepped foot in a data center before, you should recognize this. Typically, for companies hosting their own data centers, adding new components is just a matter of ordering, waiting for shipping, racking, installing OS, config, patches, applications, and later on, ready rate. It would not be uncommon for it to take a couple weeks between the server being ordered and actually ready to run your applications. So we have been able to decrease from months to weeks with machines that are getting more and more powerful, hosting applications that are requiring more and more resources. Capacity planning is getting less risky, but still, are you always using your hardware in an optimal way? Well, this is where virtualization kicks in. Virtualization is not a new concept at all. It's existed since the 60s. It abstracts what you run, the operating system and the application, from the hardware to the software. In other words, it is software that is running on hardware, pretending to be hardware so you can run your software. Thus, you no longer have a one-to-one relationship. One compute instance is now not a single necessarily computer. This is a big deal, as we can more easily optimize all the hardware that we have in our data centers. But having hundreds of servers, thousands of virtual machines, is becoming more and more common. As a result, new problems emerge. Like, how do you deploy the same code everywhere? How do you ensure that all the machines are running the same version of your application? In the late 2000s, the configuration software became popular, in part as a consequence of virtualization, since separation of hardware and software made it more accessible, and became likely that someone would just deviate the code on a node just to test. Everything was now driven by code. But still, it was not uncommon for companies to have server racks being unused, and this desire to optimize costs of compute capacity was one of the reasons the cloud was so successful. The second reason is it was the almost infinite capacity, and I believe almost as importantly, the fact that everything was API driven. That made it easier than ever to do capacity planning, and therefore autoscale. Sounds like the best we can do, right? Not quite. Virtual machines are heavy and they're slow. To this problem, yet another revolutionary solution picked up, although that was not a new concept at all. Containers have been a thing forever in BSD and Unix distributions. But they really hit the mainstream when kernel namespacing and cgroups were added and bundled in a boat that was called Docker. As they can start more quickly, have less overhead, and more of them can be packed onto nodes, they seemed like the ideal solution. But containers lead to microservices, and microservices needs orchestration. In a nutshell, orchestration turns the pieces you want with the pieces you have. So for microservices, you can define the container or containers that will constitute it with the in and the out, and more importantly, define the requirements and what makes it healthy or properly functioning. Thus, orchestration is the natural progression of abstracting our workloads from our resources. But the next question is, how do I orchestrate hundreds or thousands of containers? There are multiple solutions. If you want to orchestrate your containers, but the one that has been overwhelmingly dominating the market is Kubernetes. Kubernetes is a project that Google open sourced in 2014. It is portable, extensive, and it is a great platform for managing containerized workloads and services. Kubernetes service support and tools are widely available. It is an API-driven solution that is made out of several components. Some are acting at the cluster level, like the API server, which is the brain of the orchestrator. It is in charge of making the desired state as close as possible to the observed one. Desired state in this case is what the user wants or has defined, and the observed one is what you're actually having in your cluster. While another component is called the kubelet. Kubelet is a service that lives on every node, and it is in charge of communicating with the container runtime, whether it's Docker, Containerd, to spin up or tear down pods. Another keyword, pods. The pod is the smallest compute unit in Kubernetes. It is made out of one or more containers that share the network namespace and are scheduled together. So if you scale your application or your microservice, the bunch of containers that constitute the pod will be scheduled at the same time, and they can communicate among each other on their namespace, on localhost. The direct consequence of this is that your application are now dynamically being scheduled depending on availability and the user's desired state. Whether you want to run your application on certain nodes that have more CPU or that on certain nodes that are part of a certain group, you can do that. But from a monitoring perspective, we now have another layer to look at. The solution is to operate at all layers, as always, and leverage the overlap of information to enrich the insight you have. So you can use the Container Runtimes API in conjunction with the Kubelets API to know how a certain container has this status, whether it's OK out of memory, or it is part of this certain deployment that runs on average at 50% of the memory limit, but at 150% of its CPU limit. Finally, using the brain, the API server, which has the cluster knowledge, you will be able to know how many replicas of the image running these containers running are in the cluster. And you'll be able to identify if upscaling the deployment could avoid throttling the CPU. Now, you want to start scaling up. And Kubernetes, again, has a solution for you. The horizontal pod autoscaling, or HPA, is a natural evolution of where we have been heading for so many years. Now, there are several models of scaling too, whether it's horizontal, if you want to create more pods, or vertical, if you want to add more CPU or more memory. Kubernetes can support both. Now, a little bit of history on the autoscaling feature. It all started with the version 1.2 of Kubernetes. That was a great first step. We were able to autoscale our deployments on metrics like CPU usage. But we quickly hit a limitation. What if my application is not CPU bounded? What if I have a request latency that gets higher, but the CPU isn't moving? What if I'm using a job queue that has a backlog and I just need more instances? This queue processing doesn't involve any CPU run. Well, starting 1.6, Kubernetes introduced the support for custom metrics. You could now use any available metric in your cluster. That was a really important step. The only limitation that we hit was when we started to use external load balancers, for instance, and we wanted to use the metrics generated by those in order to autoscale the downstream applications that were supporting and responding. Well, another great news. Starting 1.10, Kubernetes added the support for external metrics. What this meant was, proven that you had a provider for external metrics, you could autoscale on anything. And that means you can use, for instance, metrics that you have in your Datadog account to autoscale the cluster and pods running in it. So it says that you can use any metric, but what is the good metric? What should you use? Let's talk about the types of metrics and the ones you should be especially interested in. We start with work metrics. The important aspect of our application is the top-level health. This can be gauged with throughput, success, error as a rate, and overall performance. You can think of these metrics as a business goal. Answer the question, how many customers are using the product or the service at this time? Then we go a layer below, and we want to know what supports or rather allows you to accomplish business goals. you will want to use things like utilization, saturation, errors in terms of resource, and availability. Another good question to ask yourself is, how high is my disk I/O? Lastly, let's not forget events. They are discrete occurrences that provide a great understanding about the system's behavior. They will help you understand the resource metrics. For instance, say someone deploys a new version of the code. How is this impacting the I/O of my instances in general? And therefore, how is this impacting my throughput? When troubleshooting an issue, you have to act recursively using those three categories. As you start seeing an issue, look at what work metrics represents the issue. Then, consider the resource metrics that support and use them as the work metric for the layer below. You can, at the same time, look at the events associated with them. And if you don't have a clear answer, you reiterate. Let's use a concrete example. If we have an online e-commerce application, we have our work metric, customer checkouts per minute. For some reason, you see a drop in this metric. A corresponding metric to the customer checkout could be the user logins. And it is supported by an actual service. If you look at the events to get the context of change, you might see errors. And in this particular hypothetical case, it seems like users cannot log in. Then, if the user login will become your work metric for the user service team that work on the login service, you will be able to associate the resource metric from this specific work metric. So the user login could be associated with the accesses to a database. And then you would be able to look at the events associated. Maybe there was a change in the code to access the DB that locked certain entries or added some load or replication latency, and so on and so forth. You go down until you find an actual reason for the top level work metric that you were measuring in terms of business. Now that we have seen the different categories of metrics, let's talk about the ones that you should care about. From the Google SRE book published by O'Reilly, there are 4 golden signals that you should monitor both in terms of work and resource. The first signal we care about is latency. A good work metric is to answer how fast is your response to users. This could be a web server metric. Whereas the resource metric associated with latency is how fast or slow are your dependencies responding to you. This could be the CDN status. The second one is the errors. You need to make sure, first of all, that your applications are generating them correctly, so you can monitor if you have any. But don't forget to monitor if your dependencies are generating any. How is an error received from a third-party provider handled in your code? Could it generate more error in your service? Think about the cascading effect and how clear you are on errors so you can identify the root causes quickly. Lastly, consider both the type and the rate of errors. If you start receiving 500 errors at a higher rate, it might mean that the service is down or bloated, but seeing a kernel panic would give completely different information. Then the traffic. What is the traffic to our application? Are you able to qualify the type of traffic you're receiving, whether it's spiky or slowly increasing from one single region? Then what is the traffic to dependencies? If your application is hosted in the cloud and you're doing cross-AZ network calls, make sure that you know well what you're going, because those can be more expensive than regular calls. If you make a change in your service or other services using the dependencies, how will this affect the overall behavior and throughput? And lastly, saturation. Can you provide downstream requests? What if you have a handful of users making heavy requests or a lot of users making very light ones but quickly? How would that affect the overall throughput and experience of your users? Are you getting throttled by any upstream request? If there is any delay introduced, can you handle data? How do you handle the latency from your third providers if they're not responding that quickly? Now that we have the metrics to use, let's discuss about how the HPA works and how does it use those metrics. Like most Kubernetes components, the horizontal pod autoscaler is a controller, and it has a main loop. This is what the pseudocode looks like. The actual HPA code is obviously more complex, but let's walk through it. So we have the main loop that checks every sync period. Sync period is 15 seconds after Kubernetes 1.12. It used to be 30, but this is configurable at the controller level. Then you can scale on different types of metrics. Whether you autoscale on external, on custom, or resource metrics, you can choose to average per pod. So that regardless of the metrics you collect from your provider, you can decide to take into account how many replica you have, which also means that you have to be aware of what metric you use and how it's computed. Lastly, it does the math. So it will take up the current metric value, divide by the desired value, and multiply by the current replicas if you're asking up to. Then round up and autoscale. So if we take an example, we have 2 pods, and we want to receive 500 requests per second per pod. But we're actually getting 1,000 requests per second. So the HPA will want to autoscale to 4. Now what's interesting to know is in terms of latency, because of the 15 seconds you are using for the sync period, but there might also be some latency to get the metric. And when you really look at the metric that you're using, pay attention to what's behind the metric. Are those average? Are those sums? Because you don't want to use the average of an average. And you don't want to use a metric that is 5 minutes old. When it scales, it will talk with another controller and other services to spin up the actual pods. But this is a standard way for Kubernetes to implement a scaling event, whether you're using kubectl deployment, scale, and then the number of replicas, or you're changing the number of replicas in the YAML file. So it is time to jump in a demo. But first, I'd like to give some context about what is going to happen. This is the setup of our application. On the right is the entry point to our users. It could be a load balancer that is connected to a Kubernetes service. When a user hits the service, either via its IP or its DNS, the request will be load balanced to one of the web servers. In this case, we'll be using Nginx. And as we start with one replica, it will serve all the traffic alone. So when we look at the logs from this Nginx box, we will see all the traffic that is received. Now we also have agents. These agents run on every node, and they will monitor all the containers running on their node. And they will monitor as well the Nginx boxes. All the metrics collected will go to our backend in Datadog. On the left side, we have the autoscaling element. So a user will create an HPA role that specifies a metric we want to use, a threshold, and a target. What is the deployment we want to autoscale given the value of the metric we collected? And then we have this key component in the middle called the Datadog Cluster Agent, or DCA. This is the application that will parse out the HPA role when it's created, extract the metric name, and query it from our backend. And then, because it's registered as an external metrics provider, it will expose the value to the controller and therefore to the API server, so that they can make a decision on whether the metric is higher than the threshold, and therefore we should auto-scale. So if I go in my terminal here, what I'm going to first show you is the cluster that we're using. So the command I'm going to run here will give me all the pods, as well as their IP, and the node they're working on. Now you can see that I'm using GKE. GKE is a really great tool if you want to create and spin up clusters with Kubernetes in Google. So we have our Nginx box here. We have there its IP. What I can do now is to describe the service that I was telling you about. That is our entry point in the whole cluster. As I describe it, what I can see is the cluster IP of my service. So from anywhere, if within the cluster I hit this IP, I will have my traffic load balanced onto this IP here. I have to respect the 8090 port that will redirect to the port 80. And now you can also realize that the IP of my Nginx pod here is the one that is part of the list of endpoints. This means that the traffic is solely load balanced onto my single Nginx box. Now, for the sake of the demo, what I'm going to do is I'm going to create a quick proxy so that I can hit from my local machine this Nginx service. This makes it very convenient, so I don't have to go into the cluster to generate traffic. I can do it live from my terminal. Now, if I hit curl as follows, you can see that I'm querying the port 9090, and then there is a very long route. This route is basically to go through the API server into the services and simply direct my request to Nginx. And then on the port named HTTP, which is the port 8090. And then I'm hitting the endpoint Nginx status. As I do this, I will start receiving the actual response from Nginx. For those of you who are familiar with Nginx web server, this is a fairly classic Nginx status. And the Datadog agent that runs on the node will pull metrics from this endpoint as well. So what I'm going to do now is to actually start generating traffic. So I'm going to do a pretty basic while loop and hit this endpoint fairly aggressively. The reason I'm doing that is because my HPA manifest here has a target for the deployment Nginx that has one replica. It uses the metric Nginx net request per second, and we have this scope. This is very useful because we don't want to get the values from another Nginx box that is reporting to our Datadog account. And finally, our target average value. Now, as I was describing earlier, it's all APIs for Kubernetes. And that includes the external metrics API. The external metrics API in this case is directed to the service Datadog custom metrics server. And what happens here is, if I look at the describe SVC custom metrics server, I have one IP, which happens to be the IP of my Datadog cluster agent here. So this is the actual backend that will respond to our metrics, the calls from the HPA controller. Another really cool trick is to query the actual values that we retrieve from the cluster agent. Now we're seeing this pretty high value, but if I do kubectl get HPA, we can see that we are now at 3 replicas. And interestingly, you can see in the logs that because I'm querying the service, I am seeing my request being load balanced onto several boxes. There is the older box that I've been using that has this old traffic. And I can see all the new boxes that are responding. And as a result, if I look at my pod, I can see that I now have 2 more Nginx boxes. Another interesting fact is the metrics being collected. As I said, the Datadog agent will collect the metrics from the Nginx box and send them to Datadog. And a good way for me to check that the Datadog agent is actually retrieving those metrics is to do a check for Nginx. I'm just going to do a grep to show this only metric I care about. And as I do that, I will basically see that this particular box is showing 595. And I have the tags as well. Now, this is very interesting because I have set my threshold at 5 in my HPA. But one of my boxes has more than 5. I think this is a really good lesson for to do autoscaling with Kubernetes. Not only should you really pay attention to the metrics you're using, but you should regularly revisit the metrics you're using and the thresholds you're using, because what works today might not work tomorrow. Let's go back to the presentation. And let's do a recap. So what did we learn today? First of all, if you're not using Kubernetes in production, you really should. Just joking. It's really the natural progression of what we're doing now. It abstracts work from resources. And when rolling any autoscaling, whether it's the rules for scaling pods or if you want to use cluster autoscaler to scale nodes, you should pay attention to the metrics you're using. Whether it's from the 4 signals, so the LETS, latency, error, traffic, and saturation, and the actual metrics themselves. But more importantly, the moral is to revisit things so they are relevant to you now, so you can autoscale properly in the future. If you've enjoyed this, there is a link to additional demos, to additional documents that you can check out to read about how we do autoscaling or the actual cluster agent. But for now, I would like to take the moment to say that this is the end of the presentation, and I'd love for you to stay tuned for frequently asked questions. We'll be back in a minute. Thank you. Thank you for tuning in. So I see some really interesting questions. The first one is, what kind of latency should I expect when autoscaling my workloads? So for this specific question, I think there are a few aspects to pay attention to. The first one is the latency of Kubernetes to autoscale. So on the version, as I said, on the version 1.12 and plus, it will refresh every 15 seconds. Now, this is configurable, but you should think about the metrics that are exposed. So if metrics are collected from APIs that are exposing metrics from 1 minute ago, they end up in your backend, and then you are making a network call to retrieve them. And as you do that, you will basically expose a metric that is slightly outdated. But more importantly, you should not rely on real-time data. Because if you start relying on real-time data and there is a blip, you might have some surprises. Rather, you should agree on the fact that an SLA could be to have a 30-second minimum and take the minimum of all your different components and then start using this as your latency expectations. I see, how do I monitor the auto-scaling activity? That is really good too. So there are a few things. The first one is Kubernetes exposes a lot of data, whether it's with Prometheus-enabled endpoints or using events. So from the Kubernetes side, you want to make sure that things are properly auto-scaled. Not that they're properly scheduled, but auto-scaled. Using the Kubernetes events for the autoscaler controller or the metrics. Then you want to pay attention to the provider itself. So is the metrics, the external metrics provider, in our case the cluster agent, exposing the right metrics, the right values? And to a certain extent also the metrics that you are using. But to circle back with the first question, if you are using an application that is bin packed, for instance, you want to make sure that the scheduling aspect is properly understood. If your application needs an entire node to run, autoscaling the application might need to spin up a new node, which might take a few minutes. So this should be added in the latency question. And how do you monitor if the scheduling part of your autoscaling? Well, whether or not the autoscaler tries to increase the number of replicas, what you really care about is, are those replicas running? So that's why I distinguished the autoscaling and the scheduling. You should pay attention to the autoscaling activity, but you should really also pay attention to the scheduling activity. I received an event to autoscale. Are my replicas up and running? What are the best practices when autoscaling? So I think the best moral is to really start playing around in staging. Use metrics that you think are relevant. Start with user stories. If you are familiar with SLO, SLIs, and SLAs, start with a user story. And then you can define what works. If you're using a metric that is directly one-on-one connected with the application you're autoscaling, that will have a certain impact. But if the metric you're using is not correlated with the number of replicas that you're targeting, you might start bumping to the maximum of nodes, of pods, when in reality you should not. So look at the metrics you have, monitor that the values you're using are correct and fresh, and every now and then you look at the activity for the past week, for instance, of autoscaling, and you want to make sure that things have behaved properly. And if they haven't, you want to update what you've been using. Learn the lesson. What happens if the metric provider is not available? That's a really good question. So on top of what happens if the metric provider is not available, I think if you're using external metrics provider, what happens if the external metric backend is not available? In either cases, in the position that was taken with the cluster agent is, if metrics are not truthful, we do not want them to participate in the autoscaling lifecycle. So you do not end up autoscaling with wrong data or outdated data. And I think that will be it for the questions. Thank you for tuning in. Please visit Cloud OnAir for more content from Google Cloud experts.